In the last video, we discussed VPC in detail. Now, in order to securely connect VPC to on-premise systems, a VPN is needed. And here are the connectivity methods supported by Cloudhub. So the first and the most common one is IPSec tunnel, which is widely used. VPC peering and direct connect are two different mechanisms, but for this you need to contact MuleSoft support. Transit gateway is a new offering wherein you have a transit gateway and you can attach your VPC and your on-premise system to transit gateway. Now in this video we will be focusing mostly on the IPSec tunnel, wherein we are going to cover all the basics related to IPSec, because IPSec is quite complicated framework and it's quite difficult to understand. So before moving into the Cloudhub point of configuration, we would rather start with all the basics. Just so you have an idea of what's going to be discussed in this video and you can decide whether to continue watching or stop, here is the overall framework that I'll be discussing in this video. So we first start with confidentiality. So confidentiality is one of the main feature of IPSec framework. Then we move on to integrity, then to authentication, IPSec protocol, and Diffie Hellman. So IPSec is a big framework and it has multiple protocols and features. So it's important that we understand each of them, because without understanding all of this feature, it's pointless. The configuration that you get would have no meaning, and although you do not need to configure as an integration engineer, but it's important that you appreciate all these concepts, because it will help you to understand how it's working. So in confidentiality we will be basically discussing about encryption and decryption and various algorithms like DES, triple DES and AES, and trying out few examples. So confidentiality is basically what we do in secure properties placeholder, right? We encrypt and decrypt all the properties, and so is being done in SSL connection, wherein the data that is being sent is encrypted and decrypted. Integrity is something that ensures that the payload is not tampered during the transit, so that can be done with help of MD5 SHA and HMAC algorithm. We'll use data view playground to explore these different algorithms. Authentication is to identify the person who claims he is. So there are two mechanisms, one is pre-shared key and the other one is RSC. IPSec protocols, we'll discuss authentication header and encryption security payload. So those are the two protocols. And Diffie Hellman is a type of asymmetric key encryption. So IPSec tunnels use this DH groups 1, 2 and 5. So we'll discuss all of them. So this is a high level overview of what's going to be discussed in this particular video. So this video will create a ground for understanding all the VP and IPSec tunnel options and terminologies, and later on in the next video we'll discuss how an IPSec actually works. So here we are understanding the bits and pieces of the puzzle, and in the next video we'll understand how we connect all the bits together and how IPSec tunnel works, and then we'll also look at a configuration from Cloudhub that needs to be configured at the other end, which is at the customer gateway. So let's get started. Confidentiality in communication can be established using cryptography. Let's go through a few basic terminologies used in cryptography. So in any cryptography you have algorithm, which are basically a steps of actions to be performed. Then we have cipher. Cipher is basically a name of algorithm, for example AES, Blowfish, DES or triple DES. Now a cipher alone is not useful. A cipher is used in combination with a key, using which we can create a cipher text. So let's take an example. So I have a string hello and I need to encrypt this. So this string, which is readable by me, is called as a plain text, and we need to convert it into a cipher text. So for suppose we use an algorithm which says shift to the right. Now how many places do we need to shift to the right will be informed by the key. So algorithm is giving me steps to be performed, but what is the magnitude of that step is being provided by the key. So shift right by 2 characters in alphabetical order. So if I apply this algorithm with this key, the output would be JGNNQ. We are shifting to the right by 2 characters. So this is the plain text and this is the cipher text. Now let's see how cryptography works in reality. So some source system, it could be a client, has to send a data to the target system, that could be a server. So the data would be in plain text. Now this plain text cannot be sent directly over the network because there are many unwanted elements who can sniff the data and can do harm. So for example, you will be sending your username and password to the server while logging in and so on. So that data needs to be encrypted. So again, you use algorithm like AES, blowfish, you use a key along with it, and using the key and the algorithm you can encrypt the data. So now this data is a cipher text which no one else can read it. Even if it tries to read it, it would be some junk value which would make no sense. It won't be a plain text. Now the data moves over the internet. Now the unwanted elements cannot understand what's the data going on. Once the data reaches to the target, now the target has to use the same algorithm along with the same key that was used to encrypt. So using the same algorithm and the same key which was used to encrypt, the target system can easily decrypt the data and the confidentiality of the data is maintained. Now if you observe, the source and the target use the same key. So the key needs to be same at both the end. So the source and the target should be aware of what key has to be used, but no one else apart from the source and target should be aware of the key, because algorithms like AES, blowfish are all standard algorithms and everyone knows about it. What the other people don't know about is that is the secret key which is used by both the parties when transmitting the data. So the key is the important element over here, and this particular mechanism where the same key is used is also called as symmetric key cryptography. Now let's understand the importance of key space. Now key space is all possible values of the key for a given algorithm. So I mean, there could be, suppose you have a 10 length string, right? So what could be the possible values for that 10 characters? In how many ways you can arrange and create keys, right? So that is a key space. For example, n bit key will produce 2 to the power n key space. So if the length of key is n bits, so it will produce 2 to the power n combinations of the key. Higher the key space, stronger is the encryption. So for example, if it's a 16-bit key, so there will be 2 to the power 16 key space possible, so which is 65,536 combinations possible. So the importance of key space is that higher the bit of the key, the stronger is your encryption, because if someone wants to hack the key, he knows the algorithm that you used, he can try out with multiple algorithms, right? AES, blowfish, it's easy to find out the algorithm, but it's difficult to find out the key. So if you use a 16-bit key, he'll have 2 to the power 16 combination which he can do trial and error and find out the actual real key which is used to encrypt. So higher the key space, stronger is your encryption. Lower the key space, weaker is your encryption. but a stronger encryption comes at a cost, which is computational cost. So if you use a stronger higher key space, then the computation cost will increase. Now let's talk about the symmetric key encryption. We have already seen in the previous slide that the same key is used to encrypt and decrypt. So the problem here is that the same key needs to be shared with the source and the target. So here the source is the Cloudhub or AWS virtual private gateway, and this is the on-premise gateway which we will need to connect with VPN, right? So in this case, both the parties should be aware of the key, which cannot be done via the internet, because if you share the key through the internet, you have already exposed yourself, right? Now someone can grab this key, who is sniffing the data packets over the internet, can grab the key, and then even if you encrypt it, there's no point of doing so, right? Because someone already has the key. So this key needs to be sent out of band, which means that you have to either physically reach to the target place and tell the people to configure this key at their end, or maybe use some other mode of communication, like give a phone call and tell the other party that this is the key, which is not a good idea. It's not scalable, and it's quite impractical, because if you initiate every transaction, and in every transaction you need manual intervention, someone to tell what is the key, right? For example, if you go to a browser, and even browser uses this cryptography, right? When you open the browser, you use keys to encrypt and decrypt the data. Now in such cases, the browser, if you want to communicate with the server, you are not going to call the server and manually tell over the phone that this is the secret key we are using, right? It has to be automated, right? So that's the problem with symmetric key. Symmetric key, when used, both the parties should be aware of it. So these are the problems. So both the parties need to know that out of the band what is the key. They cannot share it through the internet. It cannot scale because parties need to be aware of the key. So certainly it cannot be scaled. You need to manually inform the other party. Now the DES, triple DES, AES, Blowfish are some examples of symmetric key encryption. Now this doesn't mean that symmetric key encryption is useless. It's useful, it's being used heavily, and it's being used for bulk encryption, because it's faster to encrypt, because the same key is used everywhere. So a common example of symmetric key cryptography is this screen. Most of us will be using secure properties placeholder so as to encrypt the secure credentials like username, passwords, and tokens in the properties file. That is an example of symmetric key cryptography. And the algorithms that we mostly use are AES, Blowfish, right? So these are all symmetric cryptography. Now we can enter a key over here and a value. Based on that, we can generate a result which is a ciphertext. So the algorithm is AES. Let's try some values. So I'll use a value as hello and try to encrypt it. Now the key, the minimum length of key that is supported by AES is 128 bits or 16 bytes. So one character represents 8 bits. So we need to have total of 16 bytes to create 128 bits. So 1 2 3 4 5 6 7 8 9 characters, 10 11 12 13 14 15 and 16. If we give a key less than this, it will give us error. Let's try with the 15 byte string, 15 byte key length. So let's try that out, and it says that error encrypting file, invalid AES key length, which is 15 bytes. So it needs minimum 16 bytes 16 into 8 turns out to be 128. So the minimum key space over here is 128. So let's add one character and it gets encrypted. So 128 bit is one key space. After this you can have 192 bits. So if we just add one more character, it will give us error. So it should be 128 bit, 192 bit or 256. So let's make it as 192. So 192 bits will be 24 bytes. So 24 into 8 is 192, so it's 24. So this is currently it's 16, 17, 18, 19, 20, 21, 22, 23 and 24. So using this it gets encrypted. Similarly, if we increase by 1, which is we try to make it 25 bytes, it will give error, right? So again it has to be, next is it has to be 256 bits, which is around 32 bytes. So let's make this as 32, which basically means I'll copy this part and paste it again, because this was 16 and this again becomes 16, so it's total 32. So again we got the encrypted value. So as the key changes, the encrypted value changes as well. So if I encrypt it again, the value changes. So these are the different key spaces that we can use with an algorithm, and the value changes accordingly. So higher the key space, which means that it becomes difficult for someone to crack. Now here the key space is, it's 16 bytes, right, or 128 bit. So you raise 2 to the power of 128, which turns out to be a very huge value. And if someone has to crack this code, he will have to, I mean in string he can use any strings, right, like A, B, C and all characters, and to reach this value he'll have to perform 2 to the power 128 combinations to get this value, which is computationally extensive. So that's the importance of key length. Similarly, you have blowfish and DESED. So DES is not used, mostly AES and blowfish will be used, because DES is a bit it's weak from security perspective, because the key size is quite small. All this blowfish and AES have a minimum key size of 128, but DES, I guess it has a very small key size. So that's the importance. And similarly, this is encryption. Now if you want to decrypt it, you need to know the algorithm as well as the key. So if I go back, okay, I've changed it to AES, put in the value, and the key remains the same. Let's generate. So it's able to decrypt. So in the whole process, the key should be known while encrypting as well as decrypting. Using the key and the algorithm, we can encrypt and decrypt the ciphertext or the plain text. This is the list of key lengths of common symmetric key algorithms that are being used in the industry. So DES is outdated, it's not being used in the industry anymore because the key length is small. It's 56 bits only, which is 7 bytes, so it is prone to brute force attack and can be easily computed with all the possible combinations. But in reality it's 64 bits, out of which one byte or 8 bits are reserved for parity, and that is why reusable for encryption is 56, but actually it's 64 bits. So whenever you create a key for encryption in DES, it should have 8 bytes. The key length should be 8 bytes, out of which 1 byte will be reserved for parity, and that is why they say it as 56 bits or 7 bytes. Now since DES was a weak option because it has quite less key space. Now remember, key length and key space are two different things. Key length is basically how long the key can be, the minimum length requirement and the maximum length requirement of the key, which is 56 bits or 7 bytes, which means that it should have at least 7 characters. If it's a string, it should have 7 characters. So that's key length. But key space is the number of possible combinations that the key can have given all the strings are available. So the possible combination would be 2 to the power the key length in bits. So 2 to the power 56 is the possible combination for a particular key length which belongs to data encryption standard. So that's the difference. Now triple DES. Now triple DES has a slightly is better than DES because it's a bit complicated. So, and if you observe, the key length is also increasing. Now what's K1 and K3? So in triple DES, it's basically DES applied 3 times. So first it's encrypted using a key, then which is key is K1, then there is key K2 using which it is decrypted, and using the K3 key it's encrypted again. So encrypt, decrypt, encrypt with 3 different keys. Now if K1 and K3 are equal, if keys are equal, then the length is 112 bits effective length. If the keys K1 and K3 are not equal, the effective key length is 168 bits. Then advanced encryption standard. This is popular and it's the industry standard being used pretty much everywhere. So, and we saw the example for this. So 128 bits or 16 bytes, 192 bits or 24 bytes, 256 bits or 32 bytes. So it's quite complicated to crack this using brute force attack, because you can calculate it for yourself. Just calculate 2 to the power 28 and the value turns out to be a very huge value. So if someone tries to compute it, it might take months or years to compute this value. So that is why it's AES is the industry standard. Also keep in mind that the higher the key length, which means that key space will also increase, which also means that the encryption will be stronger, right? But the downside is it will be computation intensive. It requires high amount of CPU to do that. So it's always good to have a higher key length, which leads to higher key space, which leads to a stronger encryption, but it becomes resource or CPU intensive. Similarly, Bluefish, it ranges from 32 to 448. So you can have any key length ranging from 32 to 448. But in case of AES, it should be only among these 3. So that's about the key lengths of the popular algorithms or ciphers. So until now we have seen that if we want to securely send the data to our other systems over an insecure medium, we can use cryptography. We can encrypt the data and decrypt the data. But the problem here is that we were using a symmetric key, which is we encrypt the data with the same key and decrypt the data with the same key. So the problem was that we need to share the key out of band. We cannot share the key over the internet because it's insecure. So either we need to phone someone or reach out to that location and tell the key, which is not feasible and not scalable, right? You cannot, for every single time, you cannot make a phone call to the other end and tell them the key. So it's not scalable. So we need a mechanism using which we don't need to share the secret over the internet, but we should be able to derive the secret by sharing some other values. It should be derived. So for the same reason, 2 gentlemen, Diffie and Hellman, came up with a solution, and it's also called as Diffie Hellman key exchange. So let's explore that out. So I have two routers. So this will be our Cloudhub virtual private gateway, and this is our on-premise gateway. Both the parties have to communicate with each other, and they are able to encrypt the data using the shared key. But now they want this key to be generated automatically. They don't want anyone to explicitly tell the key out of band. Okay, so let's see how this is done. So what happens is, initially both the parties agree on two values. One is the generator and other is prime. Usually these values are huge, but to understand in a simple way, I have taken smaller value. So prime is a prime number and I have taken it as 19, and generator can be any value. So both the parties agree on these two values, and these values are exposed. These are being sent over the internet. Now both the parties create a random private key, and this is kept private to them. It's not being shared over the internet. So Cloudhub took the private key as 8, and on-premise gateway took it as 6. Now they calculate a public key. So this public key has to be shared with each other. So they generate a public key. So this is how they generate it. Generator to the power private key, mod prime. So generator is 3 in this case, and private key of Cloudhub virtual private gateway is 8. So 3 raised to 8 mod prime. Prime is 19. So we get 6561 mod 19. Same calculation applies to on-premise gateway. It's just that it will use its own private key. So 3 power 6 mod 19. Only difference is the private key. Both are having their own private key. So the private key, the public key is calculated based on this calculation, and it turns out to be 6 for Cloudhub gateway and 7 for on-premise gateway. Now both the parties will exchange their public key. So Cloudhub has on-premise gateway's public key, and on-premise gateway has Cloudhub public key. So until now, the values that have been shared over the insecure medium is 3, 19, 7 and 6. This anyone can snoop and find out what values are being sent. The only value that which they aren't aware of is 8 and 6. Okay, now using this public key, we can derive a shared secret. So let's see that. So for shared secret, we use the public key which has come from the other party, which is on-premise gateway. So premise public key, raise it to private key again, and mod prime. So observe that private key raised to private key mod prime is common everywhere. The only thing that changes is this value, generator and premise public key. So the private key for this router is 8. So and premise key which we received from on-premise was 7. So 7 raised to 8 mod 19, which turns out to be this value, and finally we get a shared key which is 11. Same calculations go on premise, and the shared key turns out to be 11. So both the parties now have the same shared key, which is not at all shared over the internet, right? It was derived at their own premise. It didn't go through the internet. Now using this shared key, they can create multiple symmetric keys, using which they can encrypt the data, or they can use it for integrity purposes, like using this key with HMAC. So this shared key is not directly used, but instead it's used to create multiple symmetric keys. So this is how Diffie Hellman helps us to derive a shared key using the private key, and both the parties now have the same shared key. So using that, they can create multiple symmetric keys which will be same across both the parties. So that's the idea of Diffie Hellman. Now you can also call it as asymmetric key encryption, because initially it used different private keys, right? Now private key wasn't shared, but this secret was derived out of private key. So there are two different keys being used here to reach at a shared key, so hence it is asymmetric. So any encryption activity in initial stages it is asymmetric and later on it becomes symmetric. It's because asymmetric encryption is quite expensive because you have two different keys, right? And using that it becomes quite expensive. So you use a symmetric key to get a symmetric key, and using that symmetric key you can do bulk encryption, because symmetric key is not computing expensive because it's the same key at both the end, right? So using the asymmetric key we derive the symmetric key. Now you might be thinking that this Diffie Hellman key exchange might also be used in SSL. Not necessarily. It might not be. In SSL, which is HTTPS, you might use, there could be a Diffie Hellman under the hood, or there could be RSA. RSA is yet another mechanism of asymmetric encryption, wherein they use certificates. So it's slightly different mechanism, but the end goal is same. Both use asymmetric keys and eventually reach the shared secret. Like the symmetric algorithms, Diffie Hellman also provides different key lengths. So DH group 1 is having 768 bits, DH group 2 has 1024 bits, group 5 has 1536 bits. Now remember, higher the key length, stronger the encryption, but slower is the processing, or the processing is taxing on the CPU. Once the confidentiality of data is ascertained, we need to ensure that the data in transit doesn't get tampered, and this can be done by ensuring integrity of the message. Now we achieve this by applying certain one-way function on the encrypted payload. Now this one-way function will give you an output which will be of fixed length, but this output cannot be reversed, meaning you cannot come at the input using this output, as opposed to encryption. In encryption, if you have the key, so using that output, which is the cipher text, you can reach to the original text. This is not possible in case of integrity. This is achieved mainly by using hashing techniques. So there are certain hashing algorithms using which you can create a hash code out of it. So any change, any minor change, even if you change a single character in the whole data that you're trying to hash, the final hash will change and the data is lost. So this is not reversible. Once you hash it, and if you think that using the hash code you will derive the original data, that's not possible. Everything gets lost. So here are few integrity, few algorithms which helps to achieve integrity. One is MD5, 128 bits. So it creates a converts the actual data to 128-bit value. SHA-1, which is 160-bit. SHA-2, which is 256 or 512 bits. Now let's understand the example of integrity, right? So we have two routers. One, this is the Cloudhub virtual private gateway, and this would be our on-premise gateway. Now they need to communicate over the internet securely. So here is a text, some private information that should be encrypted. So the Cloudhub router is going to send. So what it will do, it will encrypt the data. So it encrypts the data, and now it becomes ciphertext. Now using that ciphertext, it will derive a hash code, and this hash code along with the encrypted data will be sent to the on-premise router. Now the on-premise router will take the encrypted payload and apply the same hashing function that was done by this router. So it applies the same hashing function and derives a hash code. It applies the hashing function on the encrypted data, and then it applies then it gets a hash code. Now if you see, assume this to be hash code. The string hash code is a hash code, assume it. So here both the hash codes are same, identical, which means that the data wasn't tampered in transit, and it's okay if that it decrypts the data. because if hash code doesn't match, then there's no point of decrypting. It's like someone in the between has tempered the data, modified the data. So if someone modifies the data, the hash code will change. So if hash codes are different, so it means that the data was tempered. Now in this case it is not, so the integrity has been maintained. Now let's understand if someone in the middle tries to hack the data. So what can this hacker do is, he will take a data, okay, and he will encrypt the data with his own key. Once encrypted, he creates a hash out of it, okay. So and it sends the message to the on-premise router. Now what an on-premise router would do is, it would calculate the hash using the encrypted payload sent. Now since it's calculating the hash based on the encrypted payload, it's obvious that it will get the same hash which the hacker has sent. So in this case, the hash turns out to be same. So what it will do, it will assume that the message hasn't been tampered, but actually the message, it was not tampered, that's correct, but the message came from the wrong source. It's a hacker is sending the message, right? That's the problem. So this is not correct. This needs to be taken care of. Another line of thought could be that even if the hash codes over here are matching, but if someone tries to decrypt this message, if this router tries to decrypt the message, it obviously won't be able to decrypt, because the key that is being used by the hacker is different, and the key that both the routers agreed upon was different. And it makes sense and it's quite correct, but the first point is that assume, take an example that if the message originates from this router and in between the hacker sniffs the data. Now although he isn't aware of the key, but there are some mechanisms using which he cannot decrypt the whole payload, but he can modify the encrypted payload in such a way that it doesn't causes any issues. It can still be decrypted using the key, but it will slightly be modified, and it using the modified payload, which is still encrypted and can be decrypted, he will create the hash, and that hash will be sent to the other router. Now in this case, if the hashes will still match because he modified the payload and he didn't encrypt it with his own key, but it was originally encrypted by this router, just made slight certain changes which don't affect the decrypting, and in that case the message the hashes will match and the message can successfully be decrypted. And this can cause a big issue because the hacker has successfully modified the payload. So to avoid such issues, we can use hash message authentication code, also known as HMAC. Now what happens in this case is, you have the encrypted data. Now that encrypted data is combined with a shared secret. Now this secret will be known only by the two parties which are involved in the communication, and this two, the encrypted data with the shared key, will be combined and it will be passed through this MD5 or SHA algorithm for hashing, and then the hash code will be created. Now the benefit will be that even if a hacker comes in between, he won't have this shared key using which we have derived the hash code. Now since he will not have this shared key, he will never be able to create a correct hash code. So every time if the message which is combined with the encrypted message combined with the shared secret, the hash code when reaches to the other end, it will again take the message, add the shared key, and then calculate the hash. In this case the hash code will be same, but since the hacker who doesn't have this shared key, he'll not be able to successfully create a hash code. Now this shared key can be created or negotiated when the VPN connection uses Diffie Hellman, because using the Diffie Hellman we saw that we can create multiple symmetric keys. So here's an example that shows different type of hashing algorithms that are applied on an encrypted value. So this is an encrypted value. I've used the algorithm AES, and this is the key, and I've got the encrypted value. Now I've used the same encrypted value and tried to demonstrate multiple hashing algorithms. So we can use the hashing algorithms from the crypto library. So here are different various flavors of hashing. So first is the MD5. So if you see here is the MD5, then SHA-1, SHA-256. so for MD5 and SHA-1 you directly have the function which can be used, but for SHA-256, SHA-384 you need to use hash with and then tell the hashing algorithm. So it applies for 256, 384 and 512. So you just have to provide the secured hash algorithm value as the second argument. Now since we saw, right, that this algorithms are good, but they are susceptible to someone in the middle changing the data and sending out, right? So to make it more secure, we can use HMAC. So it's message authentication based hash. So in this, what you do, you use a password or a shared secret which both the parties involved in the communication will be aware of. Then you take the payload, which is the hashed encrypted payload, and then you give the algorithm, which is HMAC SHA-1, HMAC SHA-256 or 512. So these are the values available. Now notice that this hashing algorithms are converting it into a fixed length value. Even if the payload size is small, the length is fixed. If you observe here, see MD5, it's 32 length string, it's string length, so don't confuse this length with this is a bit length 256 and 384 512. all right, but if we check the string length, it's same everywhere, right, irrespective of the string. Now if I change the string to, let's suppose I'll change it to hello world, so in any case the length doesn't change, the length remains constant, it's just that the hash changes. So if I select the previous encrypted value, now if I even change a single character here, I change it, the whole hash gets changed. And observe that using this value we cannot recreate the original value. So this encrypted data cannot be recovered using this hashed value, because hashing is completely different thing as compared to encrypting. So in hashing it's only one-way function and you lose all the data. So now even if you change, suppose if you increase the length, this is test data, so if you make this, you get a different encrypted code, and using this encrypted code you can anytime reverse it, but hashes cannot be reversed. So if I change it, observe that the length remains same, length is never changing, length is always remaining same, and due to this you can never recreate the original. It's lost. Once it's hashed, the original payload is lost. You just have this hash value which will remain consistent in length, and any changes in the hash value, any changes in the original payload will result into a completely different hash code. In the integrity slide, we saw that our unwanted guest, that is hacker, was able to come into the picture and easily send message to the other party, which wasn't expected behavior, right? So he didn't identify himself, but he was still able to send the message. To avoid such issues in a VPN connection, we need authentication. So both the parties involved in the VPN connection need to authenticate each other before they start sending data. So there are basically two mechanisms used. One is the pre-shared key and other one is RSA signature. let's discuss those. So first one is pre-shared key. So what usually happens is whenever you configure VPN, so there could be one party that could be dictating the configuration. So basically what happens in AWS or also on Cloudhub, when you create a VPN connection, it automatically gives you a configuration details, and that detail will also have a pre-shared key. So one would apply the same configuration, create a similar configuration on this router, assume this to be a Cloudhub or AWS, and assume this to be on-premise. So you will have the same configuration details similar and implement in this router. Okay, and pre-shared key will be one of those. So this is how something it looks like. So in configuration, you select the DH shared key, pre-shared key, you enter it, the security association payload and proposal. So all this configuration will be automatically done over here when you initiate a connection, and then you configure same configuration over here with all these values. So what would happen is a hash value of this configuration will be taken. So I get a hash code. Now during the negotiation phases, it also sends some identity details, host type like host IP address, and along with it attaches the hash code. So hash code is the hashing of the configuration, and which has a unique pre-shared key. Okay, so this identity details are all encrypted. I mean, the host IP address and some other parameters are encrypted, and along with it a hash code is sent. So the other party gets the payload as well as the hash code. Now what it does is it also has the same configuration, right? All the proposal, DH shared key, pre-shared key, SA payload and proposal. So pre-shared key is important, so it takes the hash of this and compares both the hash, and if both the hash codes are equal, which means that this guy is one who claims he is, right? So the authentication was successful. Now other configuration a hacker can simulate, like the DH group, IP proposal, SA associations, right? Security association, but the pre-shared key is unique and it has to be kept confidential. So it's a pre-shared key, which means that it has to be shared out of band. You cannot share it over the internet. It's as good as the symmetric key that we used, which now has to be shared out of band. So you can either phone someone on the other end, or like just mail them or something, or just go at the other end and configure on the same router. So the pre-shared key, it's basically hard coding the pre-shared key, and which should not be sent over the internet, which should be done out of band, and that is how you identify each other. So this router has identified itself with this router. Now it's time for this router to identify. So in using the pre-shared key, both the parties will identify themselves. Now the problem with the previous approach of pre-shared key is that it's not scalable. You have to go out of the band and configure, although it's one-time activity and then the traffic can flow, but it's not scalable. If you have multiple routers, you'll have to go and add the pre-shared key to each one of them, right? And also rotation is quite important. So every time if you want to rotate, you'll have to change the pre-shared key. So which works many of the times, but it might be a problem for organizations, right? So to solve this problem, we have another approach, which is signature. So it works on the similar principle of SSL, or asymmetric key encryption. So let's see that we have the same DH shared key, SA payload, proposal, and then the payload that will go to the next router. So now what happens, we definitely take the hash code, but things would change here. With the hash code, we encrypt this with a key. It's a private key, right? And now what would happen is I would send the encrypted hash code. Now the hash code over here is encrypted with the private key, and along with the hash code, this router will also get a public key. Okay, and The idea is that this hash code can be decrypted using the public key. So public key of whom? This router, which is, you can assume it to be AWS or Cloudhub's router. So using this public key I can decrypt. Now this public key is basically derived from the private key. So the idea behind this key is that the private key is that anything encrypted with the private key can be decrypted using the public key. That's fine, but anything encrypted using this public key can only be decrypted with the private key. So the hash code is received, we were able to decrypt it, and then again what it does is it checks the data, creates a hash code, and then again it compares. If both the hash codes are equal, which means that this person is the same who claims it to be. So along with the encryption and decryption, it will also send its certificate, and it should be able to establish the root of that certificate, using which the authentication can be guaranteed. So in this case you don't use a pre-shared key. If you observe this pre-shared key, you ignore it. This should not be there. It won't be using pre-shared key. It will only use a DH shared key, SA payload, proposal, and other parameters, but pre-shared key should be eliminated here. So now everything is dependent on the certificates. So until now we have seen authentication, integrity, and confidentiality in communication between two routers, and this form the basic principles of VPN. Now let's understand the negotiation protocols. So the first one is IKE. So IKE is framework of protocol. It basically helps us in creating the tunnels. So it creates IPSec tunnel, which is the first tunnel, and inside it creates yet another tunnel from which the data can be transferred. We'll talk about it IKE, the phase 1 and phase 2 in a later point of time, but for now keep in mind that IKE is a framework for negotiating security parameters, and it has two phases, phase 1 and phase 2. In phase 2 it creates a tunnel, and that tunnel can hold the data packets flowing through. So for the data packets there are two different protocols. One is the authentication header and the other one is ESP. So authentication header is not quite widely used, it's very rarely used. So it only provides authentication and integrity for the packets moving. So it doesn't provide confidentiality. So overall it's not useful, because confidentiality is the main thing. The packets going through the tunnel won't be encrypted, so it's not quite useful, at least when the connection is through the internet, right? So in that case it's not useful. So although it's there, it's very rarely used, only in cases when the network is local. But it's just good to know that there is a negotiation protocol of authentication header, which is very rarely used. Now this is the main protocol which is widely used across all VPNs. So it provides all the three parameters: authentication, integrity, and confidentiality. It's called as encryption security payload. Now next is the different modes in which IPSec can run. So IPSec can run in two modes. One is the transport and the other one is tunnel mode. So in case of transport mode, assume that this is a device on this router and this is the other device. Now if it has to communicate with the other device, it will send the source and the destination address. So source will be this 10.0.0.1 and the destination will be 10.0.15.126. Now this addresses will be placed on the header of the IP packet, and this addresses will be sent as is, which means that on the internet if someone tries to sniff it, he knows the actual source address and the actual destination address. So this happens in case of transport mode. So any person sniffing on the internet will be aware of what is the actual source address. The source address doesn't change. But in case of tunnel mode, the original ID gets encrypted. So what happens in case of tunnel mode? This is the source IP and this is the destination address. So it gets encrypted, and the source address gets changed to the peer. So this is peer 1 and this is peer 2. So it eventually changed to the router, which is also called as peer, and the router's source address and the destination router's address, and the actual one is encrypted when it goes over the internet, or when it goes over the tunnel, right? In that case it's encrypted and it is the encryption security payload, and when it reaches on the other router, it eventually gets decrypted because now it's outside the IPSec. So anyone sniffing on the LAN can be able to check the actual address, but anyone sniffing on the internet won't be able to check the original addresses. So in most of the cases, VPN is used in tunnel mode and not in transport mode. So that's all for this video. I hope you found the content useful. Thanks for watching.